Hello, everyone. Let's get into Chapter 8. We are looking at molecules and materials for this chapter. We're going to be talking about solids and liquids. We're going to talk about intermolecular forces, but we're going to start off with the insight carbon. I don't always do the first section, but you know me. If it's about carbon, it's hard for me to skip. So let's start there. It also frames this chapter nicely. When we think about the properties of molecules and elements, we've been talking a lot about the atomic structure, but there are different forms of even the elements, and so the more three-dimensional structure is really important. That's why we've been studying bonding, for instance. If we look at the element carbon, carbon forms multiple different types of solid carbon. There's graphite, diamond, there's Buckminster fullerenes that was discovered as recently as 1985, and that led into the entire field of nanotechnology. Understanding the properties and forms of this material help us to choose what type of carbon we might want to use. Right? Diamond is used in drill bits and jewelry. Graphite, it's very different properties, is used in pencils. It's a lubricant, and it's a composite material. Applications for fullerenes and nanotubes are still being explored, as it's comparatively a newly known form of carbon. There's Breeze, always protecting the house. All right, so let's think a little bit more about these different forms of carbon. Phase diagrams can be useful in studying the different types of structures that are seen. Phase diagrams are typically going to show pressure versus temperature, and then you will get some information usually about the state, solid, liquid, gas, but when it comes to carbon, not all solid carbon is created equal. At lower pressures, you see that solid carbon is graphite, but once you get to much higher pressures or higher temperatures, solid carbon is in the diamond form. We may see these phase diagrams again later on. Nanotubes are a different beast, and they are repeating units of these six-membered rings of carbon in a tube-like form. They have remarkable properties. They're very strong. The tensile strength is actually higher than that of steel. And so you see different things like bicycles that are made out of carbon nanofibers because they're strong, but they are lighter than some of your metals. There's a lot of interesting chemistry that comes up when you start talking about nanotubes. But the main thing I want you to take away is the different arrangements, the different three-dimensional structures. They're all just carbon atoms here, right? But the three-dimensional structure gives very different properties. Okay, as we take that into our mind, right? Carbon can take these different forms. They're all solid, right? When you're thinking about diamond, graphite, carbon fibers, nanotubes. But it's just different arrangements of those atoms that lead to very different properties. So let's think about the different ways that solids can come together. There's two main types, crystalline and amorphous. Crystalline solids are going to be more ordered. They're going to have regular repeating arrangements. An amorphous solid is going to have a much more random arrangement. We're going to be studying crystalline solids here because they're more predictable. Amorphous solids are also important to us, but crystalline solids give us something kind of to attach onto and to study. So we're going to look at a few different types of crystalline solids. All right, to talk about the different ways that atoms can arrange in a solid, we're going to have to know some vocabulary. Packing efficiency is going to be the percentage of space occupied by the atoms, right, in a given arrangement, right? A higher packing efficiency means there's less empty space. So if you think about atoms as sort of hard spheres, like these pictures of these marbles, there are different ways you can arrange these marbles to be more or less efficient. If you just line up the marbles in these very, linear way, you wind up with quite a bit of free space here. This efficiency is calculated to be 78.5%. That means you have over 20% that's just empty space. However, if you offset your rows of marbles, right, so that the marble in the second row is kind of falling within the gap of the row above it, you get a much higher percentage, right? Less than 10% of that arrangement is now empty space. When we think about solids, though, we're not just thinking about one sheet of atoms. Typically, we're thinking about a three-dimensional arrangement. And so the way that we can start to stack these arrangements varies, right? And it gives us different types of packing. We're going to look at hexagonal close packing and cubic close packing, also known as face-centered. All right, so let's take a look at these pictures. So to get the most efficient packing, we're going to start off, right? We're trying to maximize that efficiency. We're going to start off with the offset stacking, what we saw in this slide, in this picture right here. All right, that's how each layer is going to be arranged. Now, how we start to stack those layers gives us these different close packing arrangements. Hexagonal close packing, you're going to have, you're going to have one layer, and then you are going to have, you are going to have a second layer on top, and it's going to be offset from the first. So all of the atoms in the red layer will fall into the gaps in the blue layer. And then with hexagonal, you'll have a third layer that is offset from the first and the second. So it's this sort of, if we consider this A, B, C, you have an A, B, C, A, B, C, A, B, C repeating pattern. Cubic close packing, let's go back to blue here, is going to have an A and then a B layer, and then the third layer will go back and it'll fall right above the first layer. So instead of an A, B, C, A, B, C, you would have an A, B, A, B, A, B, A, B, A. Now, both of these are considered close packing and have a 74% packing efficiency. They just have a slight difference in how each layer is arranged, right? So you will see these referenced by HCP or CCP frequently, just to abbreviate. Something that you might want to look out for as you are reading along. Cubic close packing is also sometimes known as FCC, face-centered close packing. Those are synonyms there. All right, so this is ways that our stacks of atoms or ions can be arranged to make an orderly crystalline solid. When we're looking at that three-dimensional structure, it's also important for us to talk about something called the unit cell, right? The unit cell is going to be the smallest collection, or the smallest repeating unit of a solid crystal structure, right? So if we took a solid and we took that unit cell, we could expand it in all three dimensions to get that three-dimensional structure, right? It is the unit that would be repeating. There are many different types of unit cells. You are going to be responsible for these three. Simple cubic is It's simple, as it's stated here, right? You are going to have, if you look at your unit cell, you're going to have one atom in each corner of your unit cell, right? So one atom in each corner. Now, something that is going to come up on a later slide, but let's address it right here. When you have an atom on the corner of a unit cell, only 1/8 of that atom counts. All right, so corner atoms contribute 1/8 of an atom into the actual unit cell. So when we think about the simple cubic, within this box right here, there is one atom, right? Because you have 8 atoms, each contributing 1/8 of itself into that box. When we look at body-centered is going to be much like simple cubic. You have one atom in each corner. You also have one atom in the center, right? So a body-centered atom, the whole atom is in the unit cell. So if we look at a body-centered cubic, if we look at that box right there, there are 2 atoms in that box, 1/8 of each of your 8 corner atoms, and then one whole atom in the center. Your face-centered cubic, and this is considered close packed here, or has face atoms. You are going to have, let's see, one atom in each corner and one at each face. Now, the atoms at the face are half of the atom is in the unit cell and half of the atom is in the adjacent unit cell. So contributions to the unit cell for face atoms are half an atom. All right, so if we think about how many atoms are in this box right here, you have one atom, right? 1/8 of each of your corner atoms. And then you have another 3 atoms because you have half of your 6 face atoms. So when a face-centered cubic cell, you have 4 atoms. All right, so there's better packing efficiency, as you could imagine, from face-centered cubic. There's more atoms within the unit cell. There's a little bit of how you can calculate that here on this slide. After that, something that you can skip, but you might find useful in answering perhaps a homework question, is finding the total volume occupied by atoms. You will not be responsible for this math on your exam. So I'm going to keep going. Something that is important to finish up with here is coordination number. The number of atoms that are immediately adjacent to any atom in a crystal is important because that is going to give you information about how many attractive forces are at play in each, when you look at each individual atom in the structure. All right, simple cubic has a coordination number of 6. So each atom in a simple cubic unit cell structure is going to be adjacent to 6 other atoms. Body-centered cubic is going to be 8. That one's a little bit easier to see because you have the ability to look at one single atom there in the middle, and you can see that it's going to be adjacent to all 8 of the corner atoms. So it has a coordination number of 8. That's the easiest one to visualize. The coordination of a close packed structure, so that's anything that's face-centered cubic or hexagonal cubic, they're going to have a coordination number of 12. Sorry, my dog is very excited to protect the house tonight. All right, these are numbers that you should know. This is good information about crystalline structures that you will be expected to acquire, right, to know. How these can affect our properties, right? The increased coordination number, for instance, gives you more attractive forces. That means these atoms are going to be held together by more attractive force, so they're going to be stronger structures. Each of the elements has a preferred crystal lattice, And so you see simple, body-centered, face-centered. You see hexagonal, close-packed. But you also see there's some other types of crystal structures. And when you think about the solids of each of the elements, they have a preferred crystal lattice that they form. The properties of the solid are going to be related to that structure. Let's end by thinking about diamond and graphite. Diamond consists of carbon atoms with covalent bonds to 4 other carbon atoms. And then that extends in all directions. So you've got carbon having, fairly strong covalent bonds to each atom in all directions. So it's very difficult to break off pieces of that structure, right? And that's why diamond is so hard. Whereas when we compare that to graphite, you still have covalent bonds between carbons, but now you have flat sheets, right? So that's one sheet of all of these rings of carbons. Then you have another sheet on the bottom, another sheet. And so it's hard to break apart the carbons in the sheet from each other, but it's easy to slide these sheets of carbon across one another. There's no covalent bond holding the top sheet to the middle sheet or middle to bottom. That's why it's really useful in something like a pencil. As you apply pressure, those sheets slide off. It's a good lubricant, again, because those sheets slide apart from one another.